common question I see from organic chemistry students dealing with the addition of bromine to an alkene when we get the anti-addition is why does the second bromine attack at the least substituted position? And while it may not seem important here because we're going to get the enantiomers, it can be important in more complicated synthesis. And it's important to know that even if you get the enantiomers, that does attack at this least substituted position, most substituted position, and why. So remember, in a bromonium ion, the reason this works is because the bromine has a positive charge and it does not like that. Okay, so let's for a second imagine we can, or I'm going to do this. We can remove one of these bonds to kick their electrons up onto our bromine, either this one or this one. Okay, which one would form the more stable structure? So if we pick this one right here, where we kick the electrons up, we're going to form this structure right here. And if we kick these electrons up, we're going to form this structure right here. Now, because this position or this position lost its electrons, we're forming a carbocation, where there's a positive charge at those positions. Now, which one of these carbocations is more stable? It would be the tertiary position, because a carbocation, if you haven't learned yet, is most stable at the most substituted position for reasons that we'll get into in another video. So this position right here, where we have our bromine at neutral charge again, would be the most stable because that's the most stable carbocation. Now these don't exist as discrete structures. However, what can happen, or not what can, what happens is kind of an amalgamation, or a hybrid, if you will. And so this carbon right here has more of that carbocation character, so it is more ready to be attacked.